So the next speaker is Professor Zhao from Ilinois State University, which talk about the Jacobian conjecture and the Mathieu subspace.
Thanks.
Thanks.
Okay, so the main purpose of this talk is to show how the Jacobi conjecture leads to a new concept, so-called the Mathieu subspaces. This new concept can be viewed as a very natural generalization of the concept of ideals. But unfortunately, almost nothing is known about this new concept. So in some sense, this may explain why Jacobi conjecture is so difficult, because there's some basic concept is not clear yet. Okay. So that's the main purpose of the talk. First, arrangement of the talk. First, I will give the definition of this concept called Mathieu subspaces. Second, talking about the motivations. Mainly, I will talk about the connections of this new concept with three conjectures. First, the Mathieu conjecture. Second, image conjecture. The third one is the Gaussian moment conjecture. And each of these three conjectures implies, misprint, the Jacobi conjecture. And each of the three conjectures is about a certain subspace, is a Mathieu subspace or not. So this is the motivation of this concept. Last part will be some examples and open problems on this concept. And many of them, as I said, almost nothing is known about this new concept. Okay, so let's start with notation and the convention. R in a commutative unit ring will be the base ring. K is the field, will be base field. A will be associative unit R algebra or K algebra. X, a sequence of commutative free variables. And also partial D1, D2, Dn, short notation for the partial derivative over these variables. All right, let's start with the definition. First, let's recall the definition of left ideals of any algebra A. So a left ideal I of A is R subspace or R submodule of A satisfy the following condition for any AB in the algebra. If A is in a subspace, then BA times n element of algebra A from left to A is still in I. So of course, we all know this, right? We all know this. It's basic fundamental definition. Next, let's see, we want to generalize this definition. There are many possibilities, but I don't know many. Many of them will make any sense. So here's the one which is forced in some sense by the Jacobi conjecture. So look at the definition of left ideal. In particular, we know what for any left ideal, this property is true. If we have one element A whose all powers A to the m is in the subspace I for all powers, then you time any B, an element B from left to the powers of A, and this product will be in the same subspace, right? This a special case of the property above, right, in the definition. Now, if we look at this property of left ideals, then we can make the following generalization. So replace, so for all, if we have one element A, if all powers of A in a subspace, then you time n element B from left to the powers of A, and this product or products will be in a subspace when M is large enough. So here, M is any M greater than 1, but here I only require the product is in a subspace when the exponent M is large enough, i.e., we can find a big N, which depends on A and B, the elements A and B, such that this product will be in a subspace for all little m after the big N. Okay, so this is only difference. This is only difference. Here's for all m greater than 1. Here for all m large enough. Okay. So pretty much this is what the definition of left Mathieu subspaces. This is the main idea. This is the main idea. So we require If we have one element with all powers of the element in a subspace, then what? You time element from left, sooner or later, the product will be what? In a subspace. So here, right, very easily you can write down the definition precisely. Like ideals, right, we have several cases. We have left Mathieu subspace, as we explained in the previous page, and also have right Mathieu subspace, also have two-sided Mathieu subspace. But for the left, the blue part, right, or that talked in the previous page. For the red part, right, talk about two-sided. You can time two elements, one from left, the other one from right. Then what? This power will bring the product to the subspace when M is large enough. Same token, same idea. So naturally, right, we want to read this exponent M as the time. So when M large enough, sooner or later, this product will be in a subspace. If we do that, then we can visualize the Mathieu subspace in this diagram, right? When we read M as time, this is what happens to the B times AM. This will maybe B times A, this little thing captured by power of A. Then when the time M gets larger, and will be attracted to this black part, the subspace, the black hole, right? This is the diagram picture for a real black hole in our universe. So here we get a black hole in the algebra A. Right. And look at from different angle. Yes, this is B times A to the 100, keep going to the subspace M. And two more black holes. So see the diagram, this little part attracts all the things nearby into the subspace. It's a one-dimensional black hole or one-dimensional Mathieu subspace. So this is the definition and the idea behind the definition. Couple of remarks. Unlike ideals, we have left ideal, right ideal, two-sided ideal. And for the Mathieu subspaces, we have four. Besides left, right, two-sided, also have pre-two-sided, if it is both left and right. Yeah. So formally, we have four cases, but it is not known whether or not they are really four. We don't have any example of pre-two-sided Mathieu subspaces which are not two-sided. So theoretically, right, formally we have four, but whether or not they are really four, we don't know. So I know. Two-sided also are simply called Mathieu subspaces. For convenience, in this talk, we'll just talk about two-sided Mathieu subspaces. Right, we define the Mathieu subspaces of algebras, right? For any ring, right? For any ring, we can view it as what? Algebra over Z. Therefore, right? For any ring, we also have the concept of Mathieu subspaces. So these are definitions and the remarks. So very simple, right? Very simple. Can be viewed as what generalization of ideals. So why this concept is interesting, where it came from. So this is the second part, motivations. First, let's recall the Mathieu's conjecture, which was proposed by Oliver Mathieu in 1995. 15 years earlier, before the concept was introduced. So they were in terms of Mathieu subspaces. So let G be any compact connected really group with a higher measure sigma. Let A be the C algebra of complex valued G finite functions over G. And the V is the subspace of A, consists of functions whose integral over G with respect to higher measure equals 0. So this is a codimension 1, subspace of A. Then the Mathieu conjecture claimed, right, in terms of new concept, this V is a Mathieu subspace of this algebra A. Right, this is Mathieu conjecture proposed in 1995. The motivation the Mathieu conjecture implied was the Jacobian conjecture. That's the motivation. So here we don't have to go to too much detail. I just look at what the Mathieu conjecture, roughly speaking, is just about what a subspace is a Mathieu subspace or not. So this is where the terminology Mathieu subspace came from first one, motivated by the Mathieu conjecture. Second conjecture called image conjecture. Again, before the concept was introduced. But now can restate it in terms of Mathieu subspace. So let A be any commutative Q algebra, algebra of Q, and C a family of differential operators, commuting differential operators of polynomial algebra AX of order one. Okay, we don't want to look at high order differential operators, just order one with constant leading coefficients, i.e. of the form, right? This is order one, they are derivatives. All the coefficients are constant. For the order zero part, right, you can use any polynomial you want. So all these kind of form of different operators. Suppose we have a family of commuting these kind of differential operators. Then we look at the image of these families of operators and look at the image of each differential operator, then add them up. So this is the subspace, right? Then this conjecture claims, right, the image of this C must be a Mathieu subspace of AX, the polynomial algebra of A. This so-called image conjecture, proposed in 1929, in 2009. All right, look at special case. Let psi and x be two n free commutative variables. I'll have psi 1, psi 2, psi n, then x1, x2, xn, 2n. And theta is this sequence of differential operators with theta I equals psi I minus d over xi, d over dxi. So very simple differential operator of order one with leading coefficients. Then the image of all these theta i's, add them up, must be a Mathieu subspace of the polynomial algebra in these two n variables. The special case of the image conjecture above. But this special case already implies the Jacobian conjecture. Of course, I will have to consider all cases for all n. So this is the second image, second, excuse me. Second conjecture. Again, right, this conjecture, right, even special case or the general case is just about what? A subspace is a Mathieu subspace or not. So this second conjecture, image conjecture. Third one, more recent, the Gaussian moments conjecture. So let V be the C subspace of the polynomial algebra in n variables over the complex numbers, such that the Gaussian integral, this integral, very famous one, equal to 0. So V is the subspace of all polynomials whose Gaussian integral equal to 0. And V is the codimension 1 subspace of the polynomial algebra. And this conjecture claims V must be a Mathieu subspace of this polynomial algebra. So again, this conjecture is formally, it's just about a subspace, is a Mathieu subspace or not. Then the motivation of this conjecture, the Gaussian moment conjecture, also implies Jacobian conjecture. So we have three conjectures, all of them about what? Are about a subspace, or certain subspaces are Mathieu subspaces or not. So these are motivations for the concept of Mathieu subspaces. Couple of remarks. First, the Gaussian conjecture in n variables is equivalent to the image conjecture for the commuting differential operators lambda with lambda I equals xi minus d over dxi. So again, it's a very simple and nice differential operator of order one with leading coefficients. But again, nobody knows. Nobody can prove the image of these lambdas is the Mathieu subspace. And the Gaussian moment conjecture is true for n equals 1. And even for this case, the proof is not easy. You need some algebra number theory to prove this. N equals 2 on a partial results are known. For other n's, it's completely open. So these are motivations. Three conjectures, or M plus Jacobian conjecture, then all about what? Mathieu subspaces. So of course, right, these conjectures certainly cannot be very easy because they imply what? Jacobian conjecture, but we can think about what this concept for different algebras, right? Because these generalized ideals, well, we can ask the same question, right, for any algebra, rather than just for polynomial algebras. For example, given any algebra, can we classify all Mathieu subspaces? On a few algebra, on a few algebra, we can do that. Most algebras, we don't know. Okay, not much is known. So now next, let's look at our examples and open problems. First, right, from definition, we can see easily, every ideal is a Mathieu subspace, but not conversely. So, right, a Mathieu subspace can be viewed as a natural but highly non-trivial generalization of what? Ideals. Highly non-trivial simply because, right, look at the three algebras. No? The subspaces are right in front of our eyes, but we just don't know they are Mathieu subspaces or not. We can prove, right, easily they're not ideals. That's very easy. But we don't know how to prove, right? They are Mathieu subspaces or not. If we can do that, right, the Jacobian conjecture very possibly will be true, right? If we can prove any of those subspace and Mathieu subspace, then what Jacobian conjecture is true. And actually, right, there are much more Mathieu subspaces than ideals, which we'll see, right, from other examples, right? And also theorem. So first, right, theorem is assume the base ring R is a crude domain or Noetherian domain with null field. Then every R algebra A containing the base ring R itself has at least one non-trivial Mathieu subspace. Non-trivial means what? Not zero, not what? The whole algebra. So roughly speaking, if the base field is good, is nice, then the any algebra over the R has what? At least one non-trivial Mathieu subspaces. We have a lot of algebras which has no non-trivial ideals. Right? So those are called simple rings or simple algebras. We have a lot of them. And here, right, basically says if R is a crude domain or Noetherian domain, there is no such a thing. There's no simple algebra in a sense where they have no non-trivial Mathieu subspaces. So therefore, there are much more Mathieu subspaces than ideals. Right? For example, if we choose the base ring to be Z, R to be Z, then what all the rings except Fp, the finite field, have at least one non-trivial Mathieu subspace. Now, Fp has no non-trivial Mathieu subspaces simply because Fp has no non-trivial subspace. It has no non-trivial subspace. Of course, it cannot have any non-trivial Mathieu subspace. The next example, much more concrete. Right? Look at the Q. Right? Q is a field, has no non-trivial ideals, but it has infinite many non-trivial Mathieu subspace. So fix any natural number C, then look at VC to be the set of all the fractions. B, the denominator is co-prime to C. The numerator is the multiple of C. Then what? We can show very easily V is what a Mathieu subspace of Q for any C. Conversely, we also can prove every Mathieu subspace of Q has this form. So for Q, we can classify all Mathieu subspaces. And similar results hold for the field of fractions of every PID, principal ideal domains. So another example, right? Very few these kind of examples, right? Algebras, we know all the Mathieu subspaces. Next example. Let L be an algebraic field extension of a field K. Algebraic field extension K. Then what? L is a K algebra. The V is a proper K subspace of L. Proper means not a whole algebra L. Then V is a Mathieu subspace of L as a K algebra, if only if one is not in V. So any proper Mathieu subspace which cannot contain one is a Mathieu subspace. We know a lot of them, right? Well, no, right? Any proper ideal cannot contain one. The same here. Any proper matrix subspace cannot contain one. But it can contain anyone in invariable elements, like ideals. So just for fun, well, let's see why one cannot be any proper matrix subspace. Right? This is a llama, simple llama. Let A be any R algebra with the matrix subspace of A such that one is in V, then V must be the whole algebra. Right? Since V is the matrix subspace, and all powers of 1 equals 1, which is in V, then by definition, you time any element B, right, to the power of 1. Sooner or later, right, this product will be in V. But this product is B. Therefore, any B is in V, so V is the whole ring. Replace 1 by any idempotent in the argument above, you get what? This simple llama. So for any R algebra, V is the matrix subspace of A. Then for each idempotent lying inside V, the ideal, the principal ideal, generated by E, must be contained in V. So this is a basic property, right, for matrix subspaces. And surprisingly, right, for some special case, this is also a sufficient condition. So let K be a field, A is a K algebra, that is algebraic. This is crucial, algebraic over K. V is a K subspace of A. Then V is the matrix subspace of A if and only if this property or the property in the llama above holds. For every idempotent E in V, the principal ideal generated by E is contained in V. This is if and only if condition. See, if this crucial condition, if we delete this idempotent, what happens? If for each element E in V, the principal ideal generated by E is in V. This is what implies what? V is an ideal, right? Very easy to check. V is an ideal if only if what? For each E in V, the principal ideal of E is contained in V. So therefore, you see the matrix subspaces, again, what can be viewed as what? A generalization of ideals in this way. Here, we don't check this principal idea of E in V for all elements of V. We only check special element, idempotent. If this is true, we get matrix subspace. So this property is much easier to check than what the definition of matrix subspaces. All right, next example, also concrete. Now look at the matrix algebra over a field. We know this was simple algebra. It has no proper ideals. No non-trivial ideals. Right? Then we assume the characteristic character of K 0 or what? Greater than N. Then subspace V of trace 0 matrices is a matrix subspace. Well, no, a trace 0 trace function is something really important, right, for the matrix algebra. The trace 0 matrices, or subspace of V of trace 0 matrices should be something special, right? Comparing with other codimension 1 subspaces. But V cannot be an ideal, because the whole ring has no non-trivial ideals. Now here, V is special in the sense it is a matrix subspace. A weaker ideal in some sense. And let's proof is very easy, let's skip that. So this distinguish this special subspace from other subspaces. So let K and MK be as above. This subspace V of trace 0 matrices is the only matrix subspaces of the matrix algebra of codimension 1. To really distinguish this subspace from others, it is the only one, matrix subspace of codimension 1. Furthermore, Mathieu proved for any subspace of the matrix algebra of codimension less or equal to n minus 1, then this subspace M is a matrix subspace if and only if M is contained in V. So if codimension is not very large, then all the matrix subspaces are actually contained in the trace 0 subspace. Again, from here we can tell this trivial subspace is really, really something special. Right? But this cannot be seen, right, from the point of ideal point of view. That's why this is not ideal. Okay, even for the matrix algebras, a lot of things we don't know. For example, what about other Mathieu subspecies of the matrix algebra? Now we can assume the character of K0 or what is large than n. What about others, right? Even worse, what if the character K is less than n? These are all open problems. Next example from valuations, right? Suppose we have any real valued valuations mu, right? Then what we can, for any c, right? Greater than 0, can we define VC to be all the element of A with valuation greater than c, then what? Automatically get a Mathieu subspace. This gives any real valued valuation gives a family of what? A Mathieu subspaces. This is something very useful in the algebra number theory, right? Next one, for the univariate polynomial algebra, pick up any ideal in one variable, right? Then you apply the derivative, right? The derivation, right, to the I. You get a subspace. Certainly, this cannot be ideal anymore, but it's still Mathieu subspace. So what this example said, right? It said, well, the image of an ideal under the derivation is a Mathieu subspace. Well, this derivation maps every ideal to a Mathieu subspace for this special algebra. The next example is what? Non-trivial one. Let K be a field characteristic 0, Z or n free variables cumulative. And M is what? K subspace of the Laurent polynomial with no constant term, then M is a Mathieu subspace of the Laurent polynomial algebra. So statement is very simple, but the proof is really hard. Okay, no, there's only one proof, no easy proof. It's really, really deep theorem. And that's Thomas van Kellen, the theorem above is what? The Billing case of the Mathieu conjecture. Right? You choose what the lead group to be the Torah. And this was the statement claimed by the Mathieu conjecture. Another one, non-trivial example of Mathieu subspecies. Next one is about the PDE. Right? Instead, look at what the differential operators of arbitrary algebra. Let's just look at special case. Let R be the real number, the field of reals or complex numbers. A be the R-valued smooth function over Rn. And D are these what derivations. And PD are linear, right? Either ordinary or partial differential operators of A such that P0, the order 0 part, does not vanish over any non-empty open subset of Rn. For example, like the order 0 part is a constant term, a non-zero constant term. Then the R subspace formed by the solutions of this PDE is automatically a Mathieu subspace. As long as what the order 0 part is not a 0 divisor of the algebra. So this guarantee, right, this constant order 0 part is not a 0 divisor of A. Then what the solution space of this PDE is a Mathieu subspace. So in some sense, people are looking for PDEs for a long, long time. Right? In some sense, right? When solve PDE, you can say, oh, we're looking for this Mathieu subspace. So these are examples, another example of Mathieu subspaces. Next one, open problem. Right? So recall the fact, a very easy fact, in algebra, an R subspace R is an ideal of A if only R is the kernel of some R algebra homomorphism, right? From A to an algebra B. So the ideal is closely related with homomorphism. Look at the kernel, right? You got all the ideals. Naturally, I want to ask, what are the relations of the Mathieu subspecies with the algebra homomorphism? If we look at just the kernel of homomorphism, we get ideals. Yes, they are Mathieu subspecies, but they are not all, right? There are many Mathieu subspecies which are not ideals. Therefore, we want to look at from the ring homomorphisms or other objects, such as derivations, can we construct Mathieu subspaces by taking the kernel or taking an image? And this question has not been answered yet. There are only some partial conjecture solutions. So let me mention two conjectures along this direction. So from now on, we fix a field K of characteristic 0. And in algebra A, K algebra A, denoted by I, the identity map of A from A to A. Then we see a K linear endomorphism. Dirt of A is a KE derivation of A if delta equals identity map minus phi for some K algebra endomorphism phi of A. So for any I minus phi, any linear map of the form identity minus algebra endomorphism of A is called KE derivation. And easy to verify that K linear endomorphism delta of A is the KE derivation of A if and only if. For any AB in A, we have this equation. You forget the last term, that's what Leibniz rule for the derivations. So it's close to the derivation, except it has one more term. This so-called KE derivations. They have been studied by many people under different names, several different names. So given a K-linear endomorphism delta of A, we see delta is locally nilpotent if for each A of the algebra, delta M apply delta M times will be 0 when M not enough. This is so-called locally nilpotent. And the locally finite if for each A of the algebra, the K subspace bounded by delta MA is finite dimensional over K. So this first conjecture, right? For every locally finite K derivation, the Euro derivation, or locally finite KE derivation, which came from endomorphism, delta of A, then the image of the whole algebra under this one, delta must be a two-sided Mathieu subspace of A. So the image on the whole algebra on the locally finite derivation or KE derivation should be a Mathieu subspace. So if these two, we can construct what? We can construct a lot of what Mathieu subspaces by using what? Derivation or KE derivations, right? Or endomorphism, right? Because KE derivation came from endomorphisms. And second conjecture, Ln ED, locally nilpotent ED, E derivation conjecture. So let this script little theta represent the term left, right, or two-sided, this misprint, two-sided, three cases, right? Delta locally nilpotent K derivation or locally nilpotent K derivation of A, then this delta maps every theta ideal of A to a theta Mathieu subspace of A. More explicit, right? Theta maps every left ideal to a left Mathieu subspace. Right ideal to right Mathieu subspace. This is conjecture. We already mentioned one case of this conjecture in the example. I'm sorry, example we mentioned earlier. Let me show you. Where is it? Yeah, right here. So that conjecture is true actually for univariate polynomial algebra. It maps every ideal because the algebra is commutative, right? Left to right, two-sided are same. So this derivation is locally, right? Roughly, right? It's only locally nilpotent derivation up to a constant, multiple constant. So this maps every ideal to a Mathieu subspace. So therefore, right, that conjecture is true for the polynomial algebra in one variable. Yes, yes. Right. Yeah. There are some cases right, of this conjecture are known, but for most of cases are still open. So next, I look at something known. So both two conjecture, right, I have local finite e-derivation conjecture, local nilpotent conjecture. Both these two conjectures are true for following, if the following one of the following conditions is satisfied. First, if dimension is finite. So both conjecture hold for all finite-dimensional algebra. If A is local and algebraic over the base field is also okay. And A is a Laurent polynomial algebra of K in one or two variables. So for these three, if one of these three conditions holds, then what? Both conjecture are true. Next is joined with Arnold van Ensen, the LF local finite e-derivation conjecture holds for the following algebras. First, for the rational field, a field of fractions of multivariate polynomial algebra X. The K algebra formal power series. So also true, LFED. This is the K algebra for Laurent formal power series, or just localize at X of the formal power series algebra. So for these three algebras, we have what this conjecture is true. There are many other cases also approved lately, but I will skip them. So I can stop here. Thank you very much.
Let's thank the speaker. So, any question, remarks?
I have a question.
Yes.
Yes.
Your theorem about the MES property for solutions of partial homogeneous solution of partial differential equation,
Yes.
does that situation applies to generalized functions like distribute?
I think the answer is yes. Yeah, let me see. This is a special case. So look at R. I'll choose the base string to be the field of real, the complex numbers. The general result is this one. Let R be any commutative ring. A commutative R algebra. Let D R derivations, any R derivations. You don't have to be commuting, for example. You choose any n derivations of A and P psi of polynomials in the non-commutative variable psi 1, psi 2, psi n with the coefficients in A. So I just, you write, how to say, the symbol of the differential operator in terms of psi 1, psi 2, psi n. Then get what differential operator, right? Differential operator of A. Then the only thing we need is to assume the order 0 part, P0. Order 0 part is not 0 divided of A. Then the kernel of PD is a metric subspace.
Okay.
For the general function, I think I'm not 100% sure. I think it maybe fit it into this theorem.
Okay.
Again, I'm not very sure. Huh? This is general result.
More question, remarks?
I have a question, Wenhua.
Yes.
Good to see you, by the way. I was intrigued by the conjecture that involved the Gaussian thing. Can you pull that back up? It went past me a little quickly.
Yes. Oh, sorry. Back. Gaussian.
I just didn't have time to process it.
Yes.
Yeah. Okay. So that f is a complex valued function. You're integrating over Rn.
Yes.
Okay. Yeah, that kind of comes out of left field for me. I don't see how that, not that you can explain it at the moment, but I don't see how that connects to the subject.
Connect to what? To Jacobian conjecture?
Yeah, or to the whole business about
Yeah, okay. That needs some explanation, a proof.
Yeah, I mean, I don't want to take too much time, but I just
So yeah. So roughly speaking, we used the special image conjecture. So this implies the special image conjecture. Then special image conjecture implies Jacobian conjecture.
But where does V fit into the condition? I guess I'm mystified. So
V.
V is a
How do I see that?
I mean, what does that integral have to do with V?
Yeah. Sorry, I cannot. I cannot explain. First, I don't remember. Second, it's quite long.
Okay.
It's hard for me to explain.
Okay. All right. Yeah, it seemed like there was something missing there. I just couldn't see where V.
If you are interested, you can look at this paper.
Okay.
Yeah, the whole paper is about the proof of this conjecture and plus the Jacobian conjecture. By the way, this integral is not that bad. It's not that bad. It's very similar to the factorial conjecture, right? We can, right, because this integral gives the linear functional, right? So fx is a polynomial. If we want to calculate the integral of fx, it's enough to calculate the case when fx is a monomial. Yes. So you can choose fx to be x to the alpha, right? Alpha is an tuple of integers. Then what? Very easy to calculate. Right? That basically that's just if look at, for example, in one variable case, if the exponent is odd, the integral is 0. If the exponent is even, it is factorial. So this integral, right? Because we want to consider polynomials, the integral is really it's not that hard. So we know, right, which V subspace V is. Actually, we have a basis for V by using the classical orthogonal polynomials. I don't remember, it's called Hermite polynomials, maybe Hermite polynomials, multivariable Hermite polynomials. They form a basis of V. So we know which V. We know V clearly. We have a basis. We know almost everything about this subspace V, except we don't know it's Mathieu subspace or not. So that's the difficult part.
Okay, and more casual remarks. So if not, you can thank the speaker again. Thanks, nice talk. So we resume 20 minutes. Okay.